Hi there, I'm Dr. McFerrin with DM Explains. In this video, I'm going to talk about dimensional analysis and checking unit mismatches in equations. So let's start with a procedure for dimensional analysis. Like any good problem-solving technique, we should develop a procedure. So the first step is to write the term to be converted. Step 2 is to write the conversion formula between the given unit and a desired unit. It would be unfair to ask you to remember all of the unit conversions in your head, so I have a handout for this in the video description below. Step 3 is to make a fraction which is equal to 1 of the conversion formula from 2. Step 4 is to multiply 1 and 3 together. And step 5 is to cancel any units correctly and perform calculations. So let's look at an example. Let's convert 40 yards to feet. So we start with step number 1, which is to write the given unit. Then the next thing I need to do is I need to look at the conversion factor between feet and yards. So 3 feet is equal to 1 yard, which means that 3 feet over 1 yard is equal to 1. So I'm going to multiply by 3 feet per 1 yard. And then what I do is I cancel out the yards, and I'm left with 40 times 3, or 120 feet. In example number 2, let's do the same sort of thing. I want to convert 2,700 seconds to minutes. So I'm given 2,700 seconds, and I know that 1 minute is equal to 60 seconds. So this implies that 1 minute per 60 seconds equals 1. So I'll multiply 2,700 seconds by 1 minute over 60 seconds. That's 2,700 divided by 60. That's 45 minutes. Box my answer. All right, those were relatively straightforward examples. Let's get a little bit more detailed. Example number 3 is to convert 40 yards to millimeters. Now, what I should notice from the handout that is in the video description is that there is no direct conversion that's given between yards and millimeters. So we should convert to feet first, then inches, then centimeters, then millimeters. So let's start. 40 yards. I know that 3 feet are 1 yard. I also know that there are 12 inches per 1 foot. So if I keep up with my cancellations here, I've got yards canceled, feet are canceled. I'm down to inches. And then I know that there are 2.54 centimeters in 1 inch. So the inches cancel. And then I can convert centimeters to millimeters. There are 10 millimeters per 1 centimeter. So I've canceled all of my units. Now I just need to take 40 times 3 times 12 times 2.54 times 10. When I do that, I'm going to get 36,576 millimeters. We're not going to talk in this video at all about significant figures. You probably could round this to 37,000 millimeters, but let's just give the exact answer for now. Example number 4. Let's convert 55 miles per hour, or miles per hour, to meters per second. So let's start with what I have, 55 miles per hour. Then I'm going to convert the miles first into kilometers. So 1 kilometer is 0.62 miles. Then I'm going to convert the kilometers into meters. So I've got 1,000 meters is 1 kilometer. And then I just need to convert 1 hour into seconds. So 1 hour is 3,600 seconds. So let's cancel out units here. So miles cancel with miles, kilometers cancel with kilometers, hours cancel with hours, and I'm left with meters per second. When I do this, I get 24.64 meters per second. Okay, so hopefully at this point you feel relatively comfortable with simple units, but let's talk a little bit about derived units. So, for example, I know velocity, v, is in length over time, or I could write this as length to the first time to the -1. I know that acceleration, a, is length over time squared, which is length to the first time to the -2. If I have an integral in my equation, then let's say I've got an integral of y d tau. So y has what I'll call y units, and tau has differential tau units. Then when I take the integral, this is going to equal to y units multiplied by the tau units. That's a integral. For a derivative, let's say I've got dy d tau, this is going to have units, y units divided by tau units. So we don't actually need to know how to do the differential or the integral right now, but we want to make sure that we understand what the units should be so we can check whether or not equations make sense. So let's do an example. Example number 5. If x has units of meters, what are the units of dx d big T representing time? The solution is, of course, that the units of this are meters per second. Similarly, let's say example number 6. If P has units of kilograms and X has units of meters, what are the units of the integral of P dx? The solution should be the units of P, so kilograms, multiply the units of X. So let's say kilogram meters. I put the dot there just to make that very clear. I can also use this information to determine if equations make poop. All right. One more example like this, example number 7. In this example, the units of force are newtons, big N. If the equation force is mass times acceleration, derive the units in SI form. SI would be units like kilograms, meters, seconds, and so on. So to do this, I'm just going to take my force equation. I'm going to plug in the units of each. Force is kilograms times, so kilograms is the unit of mass. Acceleration is meters per second squared. So that's kilogram meters per second squared, which it turns out is the same thing as a Newton. Last example helps us see that if I have an equation, I can determine if the units of the equation make sense dimensionally. So let's determine if the equation makes dimensional sense. Okay, so I've got velocity, which I'm expecting to be in feet per second. And I want velocity to be equal to the square root of PE over h rho, where rho is in grams per centimeter cubed, h is in feet, and then PE is in joules. So to check this, let's look at what's inside of that square root. I've got joules per feet times grams per centimeter cubed. Well, I know a joule is a Newton meter from my handout. And then I've got feet times grams per centimeter cubed. Okay, I also know that a Newton is a kilogram meter per second squared times meters over feet times grams per centimeter cubed, which is equal to kilogram meter squared times centimeter cubed over feet grams seconds squared. We need to reduce this to feet squared per second squared, so that way the square root of PE over h rho is in feet per second. Is that possible? It surely does not seem like it. So let's just look by units. Feet and meters are units of distance. So at best, I've got a distance to the first power in the top. Grams and kilograms are both units of mass. Those are to some degree going to cancel each other. And then I've got centimeters cubed. So I'm going to have distance to the first times centimeters also is a distance. So this is distance to the third over seconds squared. So I've got d to the fourth over seconds squared, which is not the same as d squared, distance squared over s squared. So not okay. This equation does not make sense. All right, so that's my video on dimensional analysis. I know it was a very quick rundown, but I think a lot of people have a lot of experience in a lot of other classes at this point doing so. If you need more examples of this, you can find a handout for that in the description of the video below. That's all I've got for now. Thanks for watching.